In band theory of solids, today we are going to discuss a very important concept of effective mass of electron. Actually, this effective mass of electron plays a very crucial and very important role in dealing with the problems of semiconductors, metals, and insulators. Okay. When you talk about the physics of semiconductors, then you will see, and I will discuss it in my forthcoming video too, that this effective mass is crucial in determining the mobility of charge carriers, you can say electrons and holes, and hence the material's electrical conductivity. Okay. We can also find the concentration of charge carriers in semiconductor using the idea of effective mass of electron. Okay. And we also see that this effective mass plays also a very important role in the dealing with the behavior of electrons in magnetic field, contributing to the phenomenon like cyclotron resonance. And this cyclotron resonance we will also discuss in our forthcoming lecture. Okay. But in this lecture, we are going to see first of all what is the concept of this effective mass of electron, and why it is needed, and what informations we get from this idea. Okay. In fact, it has been known for a long time that an electron has a well defined mass. You know, mass of whenever you ask any people what is mass of an electron, that means the rest mass of electron, you simply say that it is 9.1 into 10 to the power minus 31 kg. Okay. Actually, the value which I have just told you for mass of electron, that represents the mass of a free electron. It means an electron in vacuum, an electron which is not interacted with any other fields. Then you say that its mass is 9.1 into 10 to the power minus 31 kg. Okay. But what will happen when the electron will be accelerated inside a periodically varying potential? So when an electron moves inside a periodically varying potential, then it is seen that the mass of the electron in free space and mass of the electron in that condition during its motion in the periodically varying potential are not same. Entirely a different type of mass is associated with the electron in that very condition. So you can say that this effective mass of an electron in a crystal is a concept used to describe the behavior of an electron moving through a periodic lattice such as semiconductor or metal. Okay. Actually, in such materials, the interaction between the electron and the crystal lattice affects the electron's motion and making it behave as if it has different mass than from free electron in vacuum. Okay. So this altered mass is known as effective mass of electron. Okay. So you can say that mass of a free electron in vacuum and mass of an electron moving in a periodically varying potential, that is inside a crystal, are not same. And the mass of the electron when you consider it moving inside a crystal is called effective mass of the electron. Actually, this effective mass gives an idea that how the electron responds to the external forces like electric fields or magnetic fields. Okay. So now first of all we will find the expression for this effective mass of electron, and that will be actually a quantum mechanical expression, and how we can derive it and what the expression for effective mass actually refers, we will see now in very detail. Okay. So now first of all, let us try to find the velocity of an electron when it moves. And you know, electron is a microparticle, and whenever it will be in motion, then in accordance with de Broglie matter wave concept or wave particle duality, a wave packet is associated with the electron. Okay. So we definitely describe such an electron by a wave vector. So let us consider this k is the wave vector which will describe the wave packet associated with an electron. Okay. And we have also learnt in the wave particle duality or de Broglie matter wave concept that the velocity of the electron as a particle, or you can say the particle velocity of electron, and the velocity of the wave packet, which is also called group velocity, both are always equal. It means particle velocity is equal to particle velocity is equal to group velocity, so that there is always a correlation between the particle and its wave packet. Both are correlated only when particle velocity is equal to group velocity. So according to de Broglie matter wave concept, if the electron is moving with velocity v, then the group velocity of the wave packet Vg will be equal to v. And how this group velocity is defined? If you consider that omega is the angular velocity of this matter wave or this wave associated with the electron, then this Vg is defined as d omega by dk. Okay. But as Vg is equal to particle velocity v, so you can say that this v is equal to Vg, and that is equal to d omega by dk. Okay. Now we will see what will be this d omega by dk. Okay. And for this you have to think about about a particle or a particularly electron with moving with energy epsilon. You know, the energy of this electron epsilon can be given by a photon analogy. In de Broglie hypothesis, it is assumed that all the formula, all the results applicable for photon are exactly applicable for the material particle too. So if omega is the angular frequency or cyclic frequency of de Broglie wave associated with the electron, then energy of the electron will be given as h bar omega, where h bar, you know, it is reduced Planck's constant. H is called Planck's constant, but h bar is called reduced Planck's constant because this h bar is equal to h over 2 pi. So the value of h has been reduced by the factor 2 pi. So this is called reduced Planck's constant. Okay. Now our aim is to find this d omega by dk. So let us differentiate this result with respect to k. So you can see this d epsilon by dk will be equal to h bar d omega by dk. And so this d omega by dk, this will be 1 over h bar times d epsilon by dk. And now we will substitute this value of d omega by dk in this equation 1. And then we will get the velocity of the electron, or you can say the group velocity of the wave packet associated with the electron, and that will be equal to 1 over h bar d epsilon by dk. Okay. So you can see that the velocity of the electron is not constant, but it depends on the slope of the epsilon versus k curve. And if the slope of epsilon k curve will vary, this velocity will vary. Okay. So what is the slope of epsilon k curve, that is d epsilon by dk, that will determine the velocity of the electron inside the crystal. Okay. We will discuss this result sometime later in this video. But here only we have derived the result. Okay. Now after getting the idea of velocity of electron inside moving inside a crystal, now we will try to find uh, first of all the energy of the electron, and then we will develop the concept of effective mass. And for this, let us consider that our electron is moving in x direction. Okay, in x direction, and this electron is actually acted upon by an electric field. If you will apply an electric field in this negative x direction, then the electron will experience a force in positive x direction. Okay, and then it will move in positive x direction because electron is negatively charged particle. So you can see that force acting on the electron F is equal to minus E times E, where capital E is the electric field vector. Okay, and velocity of the electron, this is defined as dx by dt. You know, if our electron has suffered a displacement of dx in time dt, then in unit time it will suffer a displacement of dx by dt, and that is simply equal to the velocity of the electron. So here actually you can also say that this dx is the displacement of the electron in time dt. And so this v is equal to dx over dt, and so dx is equal to v dt. Now since our electron is moving under the electric field which applies a force F on the electron, okay, and it suffers a displacement dx in time dt, so the force applied on the electron by the electric field will do work. As our aim is to find the energy, so first of all we will have to see what is the work done by the applied force on the electron, because energy is the measure of the work done. So the work done by the electric force acting on the electron in time dt or in displacement dx, that will be given by delta W equal to F dot dx. But as you can see, this F vector and dx vector both are in same direction. So this scalar product will be simply F dx cos 0, but cos 0 is 1. So this will be F dx. F here is the magnitude or modulus of force vector, and dx is the modulus of displacement vector. Now let us substitute the magnitude of force vector F and the modulus of this displacement vector dx. Then you can see this work done will be equal to EE times V dt. Okay, this is the work done by the applied force on the electron. But you know from work energy theorem that the total work done by the external forces acting on a system is equal to change in kinetic energy of the system. Here our electron is gaining the energy due to its motion, so actually the energy gained by it will be simply the kinetic energy. So you can say that change in energy, which means change in kinetic energy, that is d epsilon, and that will be equal to delta W. So if you assume that there is a change in energy of electron by dE in time dt, then according to work energy theorem, this dE will be equal to delta W. Okay. And so you can say that this d epsilon is equal to E times v dt. In other words, you can also say that the work done is simply equal to the energy, increment of energy, because whenever work is done on the system, that work done is stored in the system in the form of energy. Okay. And so from here you can see that this V will be equal to 1 over E dE by dt. Okay. So you can see I have obtained here already before this expression for velocity of electron, and now considering the external electric field acting on the electron, we have again calculated the velocity of the same electron. So we can equate or we can compare these two results for the velocity. So you can say comparing equation 3 and 4 or equating these two equations, we get that 1 over E d epsilon by dt is equal to 1 over h bar d epsilon by dk. Okay. Now here this d epsilon and d epsilon will cancel out. Okay. And so we get that dk by dt is equal to E small e times capital E over h bar. Small e represents the charge of electron and capital E is the magnitude of the electric field. Okay. Now, after getting the velocity of the electron, we will find actually the acceleration, and after getting acceleration we will write equation of motion, and then by comparison we will find the mass of the electron or effective mass of the electron. So now let us see here this v of electron is defined, that is velocity of electron, and you know acceleration is simply the time derivative of velocity. So when you will differentiate this equation 3 with respect to time t, you will get the acceleration of the electron, and that acceleration a will be equal to what? That will be dv by dt. But v is this much you have seen, so the time derivative of 1 over h bar d epsilon by dk, that will be equal to a. Now we can write this derivative in this manner. This is 1 over h bar d dk d epsilon by dk times dk by dt. Actually here, first of all, we differentiate this d epsilon by dk with respect to k. But finally we have to differentiate with respect to t, so you must write here dk by dt. This is just a concept of function of function. Okay. And so this factor d dk d epsilon by dk, this will be actually the second order derivative of epsilon with respect to k. So a is given like this. This is 1 over h bar d2 epsilon by dk square times dk by dt. But we have already obtained the value of dk by dt earlier in this equation 5, and so now let us substitute this value of dk by dt, which is E over h bar, in this equation. Okay. So here at the place of this dk by dt we will use that very result, and after substituting that value you can see that a will be equal to 1 over h bar times d2 epsilon by dk square times E over h bar. Actually here this E over h bar has been written at the place of this dk by dt. Okay. And so you can see finally we get the expression for acceleration. This is a equal to E over h bar square times d2 epsilon by dk square. Okay. Now if we will talk about a free electron, it means if an electron in vacuum, an electron not moving in any field, not moving inside the crystal, and you apply the same electric field on it. Okay. Then acceleration of the electron in accordance with Newton's second law of motion is equal to F over m. But F will be equal to E, and so acceleration will be E over m. So when we talk in terms of classical concept, then we see that the electron's acceleration is this E over m. But in quantum mechanical concept, according to quantum mechanical idea, the acceleration of the electron is given like this. This is E over h bar square times d2 epsilon dk square. Okay. So both of these two equations 6 and 7 defines the acceleration of the same electron. So can you think that what is the difference between these two equations? Okay. As we will compare equations 6 and 7, then we will get a very interesting result of the band theory. And what is that interesting result? Actually, that result is for the mass of electron moving in a crystal. You can see, comparing this equation 6 and 7, we find that at the place of this 1 over m, in this equation 6, there is 1 over h bar square d2 epsilon by dk square. This is at the place of 1 over m. But is this quantity measure of free electron mass? Answer is no. This quantity in RHS does not refer to the mass of a free electron, but it refers the mass of an electron moving inside a crystal, that is moving inside a periodically varying potential. So although this quantity will have a dimension of inverse of the mass, but that is not simply the free electron mass. Actually, this quantity actually refers the reciprocal of the mass of the electron inside the crystal, which is different from free electron mass, and that very mass is called effective mass of electron. Okay, and this effective mass is denoted by the symbol m star, and so you can see this m star will be given like this. This is the expression for the effective mass of the electron, and you can see this effective mass of electron cannot be defined in classical way. It can be explained, it can be defined only using the quantum mechanical idea. When you accept the quantum mechanical behavior of the electron, and then you will be able to define it. Okay. And in a simple form, we also write this equation in this manner, taking the reciprocal of this m star, and that 1 over m star is equal to 1 over h bar square d2 epsilon by dk square. This is the expression for the effective mass of the electron. Okay. As I have told you that this is a very important and very interesting result of band theory, because in the beginning of my lecture I have told you that this idea of effective mass finds in its application in different places in solid state physics, particularly in dealing with the physics of semiconductors and the effect of magnetic field on an electron moving in a periodically varying potential, as in case of cyclotron resonance. Okay. And you can see I will discuss this result in very detail after some time in this video, but till now what we have obtained in equation 8, that actually refers that this mass m star, which is called effective mass of the electron, that is not constant like the rest mass of electron, which you write simply 9.1 into 10 to the power minus 31 kg, which is just a universal constant. But you can see this effective mass m star depends on the value of this second order derivative of energy with respect to the wave vector. Okay. And so you can say that this will depend on the value of this d epsilon by dk, which is actually the slope of the energy versus k curve. And if the slope will change, this m star, that is effective mass of electron, will also change. It will be not a constant. So this is a very important difference between the effective mass of the electron and its free mass electron, free electron mass. Both are entirely different things. Free electron mass is an absolute constant, but this effective mass is not an absolute constant, but it depends on the slope of the energy versus k curve, or you can say how energy of electron varies with k, that determines the effective mass of electron. Okay. Now this result is true or not, so we can check it, that whether we run into any problem with the ek curve, as I have told you, for a free electron. Actually, when we talk about a free electron, then we can say its velocity is simply p over m, because you know p is the momentum and momentum is mass times velocity, and p is equal to h bar k, so v is equal to h bar k over m. So for a free electron, v is directly proportional to k, or you can say that when we will plot v in against of k, then there will be a straight line passing through the origin. This will be the plot. Okay. So this graphical plot is for a free electron. Mark it. Okay. And what will be the energy of this free electron? When you talk about the energy of a free electron, that means you are talking about its kinetic energy, because a free electron will have only kinetic energy, no potential energy. So epsilon is equal to p square over 2m, and that's why we can say that epsilon is h bar square k square over 2m. Okay. So you can see that in case of a free electron, epsilon is proportional to k square. So if you will plot the energy in against of k, okay, then you can see this is just an equation of a parabola symmetric about this y-axis. So this will be the graphical plot. Okay. When k is 0, then epsilon is 0, and it increases non-linearly with k. But this is actually free electron parabola. This parabola is called free electron parabola. So in case of free electron, velocity varies linearly with k, and energy varies with k square. So it varies in a parabolic fashion. Okay. But what will happen to the velocity and the energy of electron moving inside a crystal? We will now see it. The result will be different from these results. You will mark later on. But from this expression for energy for a free electron, we can obtain the value of this d2 epsilon by dk square to compare this result 8 with a free electron. So if your aim is to write down equation 8 or write down the effective mass of a free electron, then you have to find this second order derivative d2 epsilon by dk square for a free electron. So as we have defined this energy of free electron in this equation 9, so after differentiating you will get that derivative. You can see d epsilon by dk, this will be what? This will be 2h bar square k over m, 2m, and this 2 and 2 will cancel out. So this is h bar square k over m. And so d2 epsilon by dk square is equal to h bar square over m. So if your aim is to define the effective mass of a free electron, then you have to substitute this value of d2 epsilon by dk square in this equation 8. Okay, and you can see that then this 1 over m star will be equal to 1 over h bar square times h bar square over m, because we have obtained that this d2 epsilon by dk square is h bar square over m for a free electron. So this h bar square will cancel out, and 1 over m star is equal to 1 over m. It means m star is simply equal to m. So you can see that this result which we have obtained here in equation 8 agrees. This does not contradict the result for a free electron. So it is obvious that this result is correct, okay, because it also agrees with the free electron value. So you can say that this equation cited in equation 8 does not contradict the EK curve for a free electron. Okay. Okay. But now we have obtained several results till now. But what this effective mass physically refers, how the energy of electron varies with the wave vector k inside the crystal, how its velocity varies with wave vector inside the crystal, how its effective mass varies with k inside the crystal. All these things our aim is to discuss. We have already seen that in case of free electron, this epsilon varies in parabolic fashion, as you can see in this figure, and velocity varies with k linearly. But our aim is now to discuss these quantities, how to vary in case of an electron moving inside a crystal. When you talk about the mass of a free electron, then it is not a function of k. M is not equal to k. So you can say that when we will take the variation of mass of a free electron, this is mass of a free electron, then this is independent of k and this will be a constant. Okay, but these three curves, this curve for variation of V in against of k, this curve for variation of energy in against of k, and this curve for variation of m in against of k, all these three curves are for free electron, an electron not moving inside a crystal or not in a periodic potential. Okay, but now our aim is to discuss the same thing in case of an electron moving inside a crystal. Okay, so there will be actually three curves. First, we will obtain a curve of energy versus k. The second curve will be velocity of electron versus k, and third one will be the curve representing the variation of effective mass m star in against of k. Okay, and those although I have written here this expression which is for free electron. Okay, this is for free electron, and this for Vk curve, if you talk about the free electron, then V is equal to h bar k over m. This is for free electron. Okay, but quantum mechanically, when the electron will move inside a crystal, then its velocity is given by this expression. This is 1 over h bar d epsilon by dk, which I have mentioned in equation 3. And m star, this is given by this equation 8, which you have seen here, and that is equal to this much. Okay, actually when we will plot this three quantities, epsilon, V and m star, in against of k, then we will obtain the three curves which I have shown in this figure. Now what actually this graphical plot indicates, what informations we can get from these graphical plots, you can see it. Okay, actually as I have told you earlier that for a free electron V is proportional to K. However, in the band theory, energy is generally not proportional to K square or K, as you can see it here. This is the expression for the free electron, but in accordance with band theory, the energy is not proportional to K, but for a velocity of the electron is proportional to K. I have actually mentioned it here. Okay. So actually this figure A represents the variation of epsilon, that is energy of the electron, in against of the wave vector K on the basis of band theory. Okay, you can see that variation of epsilon with K based on the band theory, which I have shown in this figure A, actually shows that the slope of the epsilon versus K curve, when you say slope, that means d epsilon by dk. And you know, if you have to measure the slope of the curve at any point, you have to draw a tangent passing touching through that point. So if your aim is to find the slope of this curve at this point, let us say O, then the tangent will be just parallel to the k-axis and slope will be 0. And again at the top of this band, actually here I have shown the first Brillouin zone. You can see here k is equal to plus pi by a and here k is equal to minus pi by a. So this region actually represents the first Brillouin zone, or the first energy band, you can say. Okay, and you can also see that this d epsilon by dk is 0 at k equal to 0. Okay, and this is also 0 at the top of the band. D epsilon by dk, you can see from this figure that this is again 0 at where? At k equal to plus minus pi by a. So at the top of the band and at the bottom of the band, this d epsilon by dk is 0, because here also this curve is parallel to the k-axis, so slope will be 0. Okay, and so in general you can say that the slope of this epsilon versus k curve is not constant, but it varies, okay, with k. Now using this variation of epsilon with k and implying the equation which I have mentioned it here, see here, this V equal to this much. So using the variation of epsilon in against of k and also using this equation 3, we can obtain the plot of V in against of k, which I have shown in this figure B. And see this graphical plot of V in against of k. Here V is actually the velocity of the electron, or you can say the group velocity of the wave packet associated with the electron. You can see that the velocity of electron is also not constant. It is 0 at this point where k is equal to 0. Actually, in all the three figures I have marked the origin by O, and this is the point where k is 0. At this point k equal to 0, you can see at k equal to 0, V is equal to 0. Okay, and also at k equal to plus minus pi over a, that is at the top of the band, or you can say at the extreme position of the first Brillouin zone, at the boundary of the first Brillouin zone, this V is again 0. Okay, but this V is equal to V max. You can see this is the position where velocity is maximum, and at this point K is equal to K naught. Okay, K is equal to K naught, and this point actually represents the point of inflection in energy versus K curve, epsilon versus K curve. This point K equal to K naught refers the point of inflection. Point of inflection. Okay, this is the point of inflection, and after which this we get a very interesting result, that when K increases from K naught, we increase the value of K from K naught, then in spite of increase in velocity, the velocity decreases. You can see velocity decreases. This result is quite contradictory to the classical result. Actually, you can say that this point, this is a very important point, that beyond the point of inflection, velocity decreases with increasing energy. Energy is increasing, but velocity is decreasing. Okay, and this cannot be understood in classical in terms of classical mechanics, because in terms of classical mechanics, whenever energy will increase, velocity will increase. Okay, so this is one of the most significant features of the band model, because this behavior is quite different that in the case of free electron model. In free electron theory, you know, if the energy will increase, then velocity of the electron will increase. Okay, because see the free electron the expression for velocity and expression for this energy. You can see that this energy is proportional to K square, velocity is proportional to K. So whenever V will increase, it means K is increasing, and with increase in K, energy will also increase. But here we see that after this point of inflection in energy versus K curve, the velocity of the electron does not increase, but it decreases. Okay, actually this gives a very important idea that after this, for K greater than K naught, it means mass of electron becomes negative. Mass of electron is negative. This is its physical meaning. It means when mass will be negative, then when you will apply the accelerating force, the particle will get decelerated. Okay, so this gives actually the idea of negative mass. Okay, and the idea of negative mass we also obtain now from the graphical plot of this effective mass m star in against of this K. And this is our prime M to discuss. This is a very important fact. You can see that the variation of this effective mass m star in against of K I have shown in this figure C. And you can see that this part of the curve, this is the curve of variation of m star in against of K. This curve shows that this curve also shows a very interesting and very important feature of band model. You can see m star is positive in the lower half of the energy band. This is actually the lower half. This is lower half band. Okay, and in this result you can see that this m star is positive. This is positive. Okay, but in the upper half band, these two regions represent the upper half band, which I am marking here. You can see in this region, since it is below the origin, so in this region you can say that effective mass is negative. This is a very important result. The idea of negative mass was first of all found in physics, and that was explained by several techniques, and that actually gives very most important informations. Okay, so you can see that m star is positive in the lower half of the energy band, and it is negative in the upper half band. Okay, and at k equal to k naught, see, at k equal to k naught, at k equal to k naught, m star is infinity. Okay, so you can see that according to this band model, the effective mass of electron may be positive, it may be negative, and even it may be infinity. Okay, so I have actually mentioned all these facts here, that you can see. I have shown that this in Vk curve I have written that V is 0 for k equal to 0 and at plus minus pi over a, because at those points you can see that this slope of the energy versus k curve is 0. Okay, and this V is maximum at k equal to k naught. You can note down these things in your notebook. Okay, and one thing I have not tell you, that this maximum velocity of electron is just equal to the free electron velocity. This is also a very important fact. Okay, and beyond the inflection point the velocity decreases, as I have told you, and with increase in energy. This is one of the most significant features of the band theory, because this behavior is quite different from the free electron theory. And as I was discussing just now, the variation of m star, and you have seen that m star is positive in the lower half of energy band, m star is negative in the upper half of the energy band, and m star is infinity at k equal to k naught, that is at the point of inflection. Okay, now before explaining the physical significance of this negative mass, I would like to introduce you a very important factor which is denoted by the symbol Fk, and this factor you will see later on in my next video on the distinction between metals, semiconductors and insulators, that it finds a great importance in dealing with that problem. This factor f of k, Fk is defined like this. This is defined as the ratio of m and m star. So actually this Fk is the measure of extent up to which an electron in k space behaves like a free electron. Okay, and as 1 over m star is 1 over h bar square d2 epsilon by dk square, so Fk is equal to m over h bar square d2 epsilon by dk square. Okay, now if you say that Fk is equal to 1, then you can see this equation here. This will be equation 8, 10. This will be actually equation number 11, not 1 but 11. Okay, so m star will be then equal to m. That is, in this if Fk is 1, electron will totally behave as a free electron. Okay, so Fk decides the electron will behave as a free electron or a heavier particle or lighter particle. That is completely decided by this factor. But if you consider that Fk is less than 1, then you can see this equation 11, that m star will be greater than m. In this condition, the effective mass of electron is greater than the free electron mass, and so the electron behaves like a heavy particle. But if Fk is greater than 1, then the situation will be just opposite, and then m star is less than m. It means the effective mass is smaller than the free electron mass, and so in this very condition, this electron behaves as a light particle. Okay. Now we are going to see the most important fact, that which is physical significance of this negative mass of electron. Actually, this physical significance of negative mass of electron can be explained on the basis of three aspects, or in three ways we can explain it. Okay. You have seen that negative effective mass of electron in upper half energy band physically indicates that the electron behaves as a positively charged particle. Because why we say that electron behaves as a positively charged particle? Because in that region you can see the field which was accelerating the electron up to k0 to k0. Now the same field is decelerating the electron, but electric field on the electron acts in acts in opposite direction. The electric force on the electron acts in opposite direction of the field. So the field which was accelerating the electron, now it is decelerating the electron. It means the nature of charge has been changed. Now the electron has, now the particle has become positively charged. So actually, this negative mass implies physically that electron behaves as a positively charged particle. In fact, that positively charged particle is called hole, and hole is nothing. This is actually the absence or vacancy created by the electron. When an electron is absent from its site, at that site a positive charge is developed, and that behaves like a mobile particle, and that is called hole. Okay. So in this way, this negative effective mass gives the idea of hole, and knowing the concept of hole, only you can explain the physics of semiconductor. The solid state physics of semiconductor can be explained only on the basis of concept of electron and hole, because in semiconductor you will see there are two types of charge carriers: positively charged holes and negatively charged electron. Okay, and this idea of hole is obtained by the concept of this negative effective mass of electron. Okay. And I have also earlier told you that we can obtain the explanation of this negative mass from the Vk curve. As I have told you that when we consider that our electron starts at this point k equal to 0, then you can see its velocity increases with increase in k. But this increase in velocity is up to k equal to k naught. K equal to k naught. But after k equal to k naught, that is beyond k equal to k naught, this velocity decreases. So this decrease in velocity is just equivalent to saying that the mass of the electron is now negative. So I have mentioned it, you can see. Let us suppose that electron starts at k equal to 0. When an electric field is applied, the wave vector k increases. The wave vector k increases linearly with k. Don't worry, the page has been turned, but this will be just okay. Okay, increases linearly with time until the velocity reaches its maximum value. Okay, maximum value. And the electron is accelerated by the field. Beyond the maximum, the same field produces a decrease in V. This means that mass becomes negative in the upper half of the band. Okay, I think we have cleared, because I have already explained this fact. Okay. Actually, this negative effective mass is also explained on the basis of Bragg's reflection. In fact, due to Bragg's reflection, this K is when the K is close to the value plus minus pi over A, that is at the edge of the band. Then a force applied in one direction leads to a gain of momentum in the opposite direction, and so that the mass becomes negative because the momentum is increased in opposite direction of the applied force at this boundary of the band. And so so you can say that as according to Newton's second law of motion, increment of momentum should be in the direction of force, but here increment of momentum is just in the opposite direction of force. So how it is possible? It is possible only when we take the mass negative. So in this way we can also explain this negative mass of electron on the basis of Bragg's reflection. Okay. Now, till now we have discussed two concepts. First of all, we have discussed the free electron theory of model. Then we have seen there are so many shortcomings, so many drawbacks of free electron theory of metals, and free electron theory of metals is particularly limited to the properties of metals, not for semiconductor, not for insulators. Then we have learnt about band theory. Okay, but you will be get surprised that all the results of free electron model can be utilized, can validate the band model only simply replacing the mass of electron by its effective mass. So if you will replace mass of electron m in any result of free electron theory of metals, then that result will be same as that obtained from the band theory. Okay, and so in this condition you can say all results of free electron theory of metals may be incorporated in more realistic band theory merely by replacing the electron mass m by the average effective mass m star at the Fermi surface. Okay, this is a remarkable fact. At the Fermi surface you have to replace m by m star, then all results will be valid. Okay, and in this condition what will be the Fermi energy? If your aim is to now write the expression for Fermi energy, you will write the same expression, only difference will be that m will be replaced by m star. So EF in this case is h square over 2m star times 3n over 8 pi v whole to the power 2 by 3. Here you know n by v is number of free electron per unit volume. So this is also called density of free electron or density of valence electron. Okay. So this was the concept of effective mass of electron, and we will use it, as I have told you, while we study the semiconductor physics and the magnetism in solid state physics. Okay, so I hope you have definitely enjoyed this lecture very much. Thank you very much.